All right, thanks everyone. This is my first time at Flatiron, so this has been great. I'm pretty sure I'll be coming back again. I know I'll be coming back again in 2 weeks for the Foundations Model Workshops, so I'll be seeing you again soon. So today I'm going to talk about a somewhat niche topic, which is how do we extract information from noisy spectral cubes? And you might think this does not apply to you, but it turns out this is a very general and broad problem that I hope that some of the tools I talk about will be of interest to your science as well. All right, so one of the machine learning topics I have been obsessed with for quite some time is what is the best way to cluster data, right? Why do we care about this? Well, the idea is that if we can identify structure within the data, that structure can tell us something about the underlying physics of that data, right? That's what we want. So this crops up in a number of different areas in star formation. We'll call it the star formation blob. So for example, you might want to know, what is the star formation rate? All right, well then you got to count the rate of formation of new stars relative to some gas reservoir forming those stars. You might also ask something like, what is the star formation efficiency? Again, now that's counting just the number of young stars formed over this gas reservoir, right? So the problem comes in with what is this M gas and how do we define it? So there's been a variety of different techniques that have been developed. In this particular beautiful FANGS image, a group went in and applied dendrograms, which I'll talk more about, to identify all these clouds, which can go in the denominator. So this problem of these very simple questions, star formation rate and efficiency, becomes what defines a molecular cloud? So this is essentially a clustering problem. Other star formation questions you might care about is what sets the stellar initial mass function? What gas actually goes on to turn into stars? And this seems to be related to these dense cores. We look for the densest regions, the one we think are probably star forming, and then there's some efficiency factor between this dense gas and the stars that are formed. All right, so here's the Pipe Nebula. This group identified dense cores within the pipe. This is relatively older work, but some of the first work that pointed out that there's this very interesting similarity between the distribution of core masses, as identified in a region like this one, and the stellar initial mass function. There seems to be this constant factor mapping. All right, so now we get into the problem. What defines a dense core? Also a clustering problem. So given that there might be some relationship between cores and stars, you might then want to know, how does the IMF vary with environment? Here's this beautiful image of the brick. And people have looked at regions like this one, which are much more extreme than our local star forming clouds. And once again, look for structures within this cloud to determine what the future star formation might look like. In this case, the distribution of core masses seems to be a bit flatter than saltpeter, which maybe suggests there'll be more high mass stars forming. But again, this is really a clustering problem. And what you get out of this is based upon how good your clustering method is. All right, so what I'm trying to tell all of you is that in star formation research, it's clustering all the way down, okay? All right, so then you can ask, all right, well, we've been doing this for quite some time. We've been identifying cores and clouds and clumps. So what about these classical statistical approaches that everyone uses? All right, so first there is clump find. Probably a lot of you have used this yourself. If any of you use clump find? A few of you, okay. Yes, those of you who've been around longer have used clump find. I would say this is the OG of star formation structure identification. So this is a watershed decomposition algorithm, so-called, you have peaks and valleys. If you pour them water in, then it flows to the minima. But in any case, from the abstract of this seminal paper, clump find is an automatic objective routine for analyzing the clumpy structure in a spectral line, position, velocity data cube. So basically, you have some RMS noise within your cube. You contour the data according to that noise. You search for your peaks, so you need a peak finder. And then you determine which peaks are significant, and you follow this to contours to lower intensities. As the contours connect, you segment the data, and those become your clumps. So a more recent method is dendrograms. So we can call this the Kendrick-Lamar upstart for the clustering algorithms. So this too is also a watershed decomposition algorithm. From the description, the dendrogram of a data cube is an abstraction of the changing topology of the isosurfaces as a function of contour level. And so there are a lot of similarities between this method and clump find, the main difference of which this is hierarchical. So again, we identify all distinct local maxima. We contour the data, identify the isosurface between each pair of maxima. We determine if those maxima are well separated and distinct. And then we go down our tree with these much more finer contours and basically refine until our hierarchical structure, each branch has not more, not less than 2 leaves, okay? So this works differently than clump find because now we understand the hierarchy of structure within the data, and we can get sub-portions of the data, these leaves, right? So we don't have to force all of the emission into different leaves within it. We can leave it behind as some kind of background, for example. All right, so people have been using this for more than a decade. Watershed decomposition algorithms are quite old, but there's some more recent work that Alyssa Goodman pointed out. You know, dendrograms should be much, much better than clump find. And one particular problem is that clump find tends to over-segment the structure. So here's a star-forming region, dendrogram, and what you get when you clump find, apply clump find, you can see there's a lot more substructure. In particular, in this paper, she argued that clump find identified structure does not correlate with physics. And as evidence, they looked at the properties of these leaves, these bowling balls here, and found that these are the ones that are self-gravitating. So the idea being that dendrograms are identifying real physics when they produce this tree. Whereas when you look at the clump find segmentation, there's nothing particularly special about these 4 regions within the cubes. But dendrograms also have their weaknesses. So this is from a paper I collaborated on with a student, Rachel Smolin and Caitlin Cratter. There are also perils of dendrograms, okay? And as an observer, you get one snapshot. So you can't really assess how those contours and structure evolve with time. You just get one application of it. But in simulations, we can do that. We can identify the dendrograms, follow them over time, and see how the structure evolves. All right, so in this paper, we dendrogrammed these turbulent MHD simulations, right? Identified cores. We found that when we did that, the core mass function at all of these different snapshots was preserved, right? But this was hiding something underneath, was that at every given snapshot, each core was defined a little bit differently. And so this is, in some sense, a random Gaussian process where all the cores change for each snapshot, but the function still looks the same. All right, so that's not good. And what this was telling us is there is significant variation in time. There's no time-stable isocontour. So if you follow any individual core, you can see these very large variations. And this is coming because you have some slight change in the peak, you know, it collapses a little bit more, or maybe loses some mass, and that changes all of the contours, which change all of the mass being associated with those contours. So I revisited this with the star forge simulations, and we did maybe a bit better job here because in StarForge, we did this dendrogramming on the raw data. All the cells have IDs. We were able to track them exactly, find out where the mass went. Moreover, it turns out whatever star formation you're doing, there's a lot of merging and splitting of structure. This just naturally happens, the gas fragments, or it merges because you have things flowing along the filament. So we built a graph of all of our cores, where the cores were nodes, each with a vector property, and then we traced the graph to maintain the mass of the structure as consistently with time. So when you do this, you get a bit better time stable information, right? You can see there's some trends with time for these 8 random star forming cores, but you still see that there's a variety of different peaks that are happening, particularly in the prestellar phase. All right, so this is sort of depressing. Okay, it's sort of depressing. So we get back to what is the best way to cluster data? Okay, so what is the problem with these approaches? What do we have to fix? All right, the first thing is that the data that we're working with, say spectral cubes or simulations, are very high dimensional. So this is the B5 star forming region, and it should begin to rotate. There it goes. Yeah, so this is actually position velocity. And you can see there's a lot of complex structure in here that's connected. This is actually outflows sticking out. Moreover, aside from being high dimensional, this is not nicely described by a simple model, right? So when you're trying to peak find and core find, like you're trying to, in some sense, encourage your data to be Gaussian, and it is not really. And so you have this complexity there. The other problem that you don't see from that particular cube is that these data are actually very noisy. And often what we do when we analyze this data is we threshold it and we ignore all the information below, say 3 sigma. We say, okay, just forget about that. All right, you see there's a huge amount of noise here. The other problem, of course, is that we have limited resolution and instrumental effects, right? So if we had infinite resolution, we could actually see that this is not 1 cat, but 2 cats, right? And so we would like our method to be able to be as sensitive as possible, to be able to sharpen the detection of structure, right? But this is not what we have. We don't have these sharp cats. We have very smooth, blurred cats, right? So it's hard to tell how many there actually are. You guys think you're here for a talk on clustering, but you're here for a talk on cats. You'll realize this soon enough. Okay, so this brings me to machine learning, right? So we can solve everything with machine learning. Yeah, you laugh. Okay. Yeah, I was very optimistic early on. But in any case, so I'm going to talk about 2 different ways in which we're trying to tackle structure identification with machine learning. So I'm going to talk about a supervised approach and the unsupervised approach. So the supervised approach is essentially one of labels, right? You need some ground truth. You need some training data. The unsupervised one is one of parameter setting, right? So if you can intelligently choose your parameters, then you are much freer from bias. Moreover, if you're intelligent with how you do the unsupervised approach, you can also deal with the problem of high dimensionality, which can be a bit harder in the supervised case. All right, so we're going to enter into this through constructing a training set. So when I got started on this, the structure that I was particularly interested in detecting was stellar feedback, right? So these outflows and winds, you can see we're trying to detect this very complex structure in this very smooth data. So when we approach this from the supervised approach, we don't have a nice analytic model, so we have to create some models. So we can do this with numerical simulations. And these are some older simulations using the Orion code, where we have this turbulent magnetized gas. It looks better online. It's very gray here. And we put in some stellar winds, and they expand, right? But this gives us a nice training set. So basically, we take our hydrodynamic simulations, we post-process them to get the observables, that is, we perform radiator transfer on them. We add in our noise and instrumental effects. And then at the end, we have our set of training data. So basically a large realistic set of data that's complex and has accurate labels. So one thing I should mention in these codes, the nice thing is that we have tracer fields. So they trace out the feedback. And so we have exact ground truth. We know at every point where the outflows are. We know at every point where the stellar winds are. And this gives us very nice labeled data. All right, so we can take our training set and we can feed it to a machine learning algorithm. In this case, a convolutional neural network. This is a UNet architecture with a few hidden layers. So this is pretty generic, but if we make enough training data, we can train this neural network to find structure. Okay. So the first case was applying to slices. This is, you can actually clearly see all of the feedback in these cubes, right? Like, you know where all the bubbles are. That's a joke. Actually, so they're kind of in here. And we can use these labels to train it, and then we can hold back some data, which we can use to validate our approach. So this is synthetic training data, synthetic test data. All right, so it does pretty well. The true positive is some shells. That's where it's getting it right. False positive is in purple, so it's mostly in the boundary of that correct case, and then false negative, where it's missing some of the shells. All right, so it turned out when we trained this, it performed horribly on real data, by which I mean it did not work at all. So we thought about it and we thought, okay, what's the problem here? The problem is fundamentally where you're doing structure identification, if a human can't find it, the algorithm can't find it. Okay, so what was the missing ingredient? The missing ingredient is that structure is fully connected across 3 dimensions. It doesn't just have a morphology, it has some dynamics, right? And so within that dynamics is some physics, which then allows us to create a unique signature, which we can train it to identify. So we modified our network to be a 3D convolutional neural network with a 3D convolution across those pixel position velocity channels. And then it worked. So this is an actual bubble in the torus molecular cloud. We didn't find it with our algorithm. It was already there. It had been human identified. But what we get out of this is that we get a much more specific prediction for where that bubble is, where it begins and ends. And if you look at the emission as it's going around, you'll see that our method is excluding emission that seems to not be part of it. For example, it's below, above and below the bubble, and it's giving us this more accurate view. So we were very excited about this. So of course, the next target was protostellar outflows. Again, this B5 has not just a bubble there, it also has outflows, which we saw. And this was nice because we already had a human created catalog. So here's the star formation blob at work. These are all clearly protostellar outflows. Yeah, so these are actually hard to find. The way a human finds them is you load up your spectral cube and you scan through the channels, and then you one by one make specific velocity cuts to identify where that outflow is. So this is a really annoying human analysis problem. But if a human can do it, we can train the machine learning algorithm to do it. So we made a training set with protostellar outflows. Again, we know exactly where they are. We trained 2 models, one to predict the emission, that is, what is the emission that's participating in that feedback, the outflows, and one that solved the inverse problem that says, given this emission is participating in the outflow feedback, what is the mass that's producing that emission? All right. So here's the test synthetic observation by eye. Both models do pretty well. And here's the model applied to a real Perseus outflow, right? So you can see this elongated structure there is being picked out as an outflow. There's a cluster up here with some other outflow activity, which is also being picked out. So this is what this looks like in 3 dimensions. Okay, we'll rotate it. And you can see the outflows of the things that are sticking up above and below the cloud. And importantly, our model is excluding this sort of chance alignment fluff that is actually not part of the outflow, but is moving at the same sort of low level velocity where those outflows are. So this would be like the core emission rather than the outflow. You can see there's some extra fluff that is also picking up, and we spent a lot of time training our model to reduce sort of additional things. And by and large, it does pretty well. So if we go back to this, we find that it identifies all of the outflows we think it should. These are the red and blue shifted projected lobes, still looking extremely blob-like. The young stars there are marked. And so it identified all 60 previously visualized outflows that were in Hector's catalog. Then it identified 20 new outflows, which we confirmed visually to say, okay, yes, these are definitely outflows. And for free, we get an estimate of outflow activity in the confused region, where it's really hard to determine what is actually happening, to pick out a clean signature. Okay. Now, then people at this point sometimes say, well, but then what driving source, what is driving each of these outflows? And the answer is, I don't know. That is hard. We can't do that in the human perspective. The machine can't do it. Maybe we could try and train a method to do it, but it's really hard, particularly when your census of YSO is incomplete. So it's really hard to attach a particular outflow with a particular driving source. Okay, supervised takeaways. Okay, so these CNNs provide a really fast, flexible, automated way to identify 2D and 3D structures. What we get out is a map, pixel by pixel map, prediction, not a catalog. You would need more data segmentation if you want a catalog. Through this work, we did censuses of Taurus, Perseus, Ophiuchus, and Orion clouds. And with our inverse modeling, we can basically calculate the total mass, momentum, and energy associated with these features. We find that this feedback is enough to maintain turbulence, but not disrupt the cloud, right? So these are stirring the cloud, not disrupting it. In general, the new outflows were basically very similar energetically to the ones humans identified, but there was a very strong correction for the stellar winds. That is, when humans identify the winds, very hard to pick out that from the background cloud. And so our method is able to make a prediction that separates out some of that contaminating emission and reduces their impact by a factor of 10. All right, so that's well and good. But that was really a lot of work. That was a PhD thesis to do all of this. And, you know, a lot of the effort, instead of looking at the data, was in building up this training set. You want your training set to be as close to the real data as possible. But the problem is you don't know what the properties of that real data are. You don't know what the average density is. You don't know what the average temperature is. You don't know what the abundance distribution is, which means you have to build a rather very large training set that's broad enough to span your conditions. Now, as you may have noticed, I also didn't talk about uncertainties. And so our method is not giving us confidence estimates, except in the sense of we test it on out of distribution data, which is never seen before. And that allows us to say, okay, if the conditions are wildly different, then we get maybe a factor of 2 or something in the estimated mass. And it is also dependent on the input simulations. So I am constantly getting this question, which is when I give people this look. So how do you know the simulation is good representation of real data? I hate this question. When this is StarForge data, of course, I say it's exactly like the real data, right, Mike? It's yes. And so I'm not going to talk about how we've used StarForge for training machine learning methods in this talk. But whatever you're working on, this is a problem you have to grapple with a lot. All right, so we can do a correction and switch to talk about unsupervised machine learning. So we're going to move away from trying to find a model with labels and just ask, what is the data telling us about the structure within it? So I'm going to tell you about a new approach, multiview, prototype, embedding, and clustering MPEC. So back to our data you saw before. This is ammonia data from the Green Bank Ammonia Survey or gas survey. Again, we see it's very messy, blobby with lots of noise. Okay, if we go from scratch with machine learning, what you would do, what I would do, what you would do, is you would go to scikit-learn, and then you would say, all right, find me a clustering algorithm. There's so many choices. Surely one of these can pick out structure intelligently. It turns out that very few of these can handle clusters that have different shape, size, density, compactness, and separation. You can't probably read most of these. You can see HTB scan, DB scan are over here. You have Gaussian mixture model. If you look closely, you can see that almost all of them fail terribly on one of these very simple problems, right? Things are being what you would classify as 3 things by eye or 2 things by eye are being segmented entirely incorrectly. But one of these is actually a bit better than the others, and that is spectral clustering. Has anybody used spectral clustering? Good, you won't ask me any hard questions about it. I love this. Okay, so spectral clustering is actually a graph-based clustering approach. So what you do is you build a graph where your vertices are your data points, and the edges that connect the data points represent some kind of similarity between them. So that could be like a Euclidean distance. You can plug in your favorite similarity, okay? Now, there's a very large subfield of statistics for dealing with graph-based analysis and proofs and so forth. So there's a lot that we can use here. Okay, so the way the clustering then works is you look at your graph with your edges, and then you cluster based upon those weights and those edges between the different nodes of your data. There's a variety of different graph clustering methods, which you may have heard of. There's graph neural networks, stochastic block models. I'm going to talk about walk trap, which is a Markov-based approach. Okay, this seems promising. There's one last piece here, which is that the data sets that we're working with are large. And the one thing about doing graph-based machine learning is you have to build your graph, which usually goes as n squared. So that means you quickly have a very large graph that you're trying to analyze, which can become unwieldy if you're starting with tens of thousands of data points already. Okay, so what we need is a smaller, more efficient graph. And there is something that helps us, which is called vector quantization, which is a fancy way of saying we're going to find a smaller subset of data that represent the larger set, right? They're called prototypes. So the idea is we find a smaller set of representative data and proto, much, much less than the actual number of data points. Then we build our graph with this and we work with this data. So instead of this space with the raw data, we work on this space with the prototypes. So this has the advantage of it reduces our sample size. It reduces noise in a way you'll see much more clearly. You can kind of see by eye, it's much less noisy. You'll see that effect later. But the other thing that vector quantization does is that it gives you a graph for free, something called a CADG, a cumulative adjacency graph, which basically gives the total number of connections between points. And you can use this as weighted, you can define a weighted metric that tells you and encodes the significance of the correlation between the data. Okay, so it's kind of like an intelligent k-nearest neighbor graph, but basically you're building a graph where now your prototypes are the vertices, okay? So go back and forth, looks like this, right? This is what you get for free from the prototype distribution, right? So it's a low dimensional encoding in a graph. Okay, so next you might say, okay, that's great, but then how do you find this magic data? How do you find this magic set of prototypes to use for your efficient graph? The very common thing people will do is k-means, right? So you take your data, you define some k number of clusters, and you cluster it, and each of those clusters, you can like average that data and gives you a nice prototype. But you see the problem here is that you define k, so you cluster the data in order to cluster. And there's something that seems quite wrong about that. So in fact, k-means, which again requires an input number of clusters, is not good for this. So we're going to use something called self-organizing maps. So this is essentially a neural network-based approach, but what it gives us is a low-dimensional representation, a graph and a set of characteristic regions, which we can define as prototypes. Okay, so this is actually the RGB cube, arguably extremely smooth data projected into a two-dimensional lattice by the self-organizing map. Okay, so our astronomy data are smooth, but not that smooth. So we're going to start out with a different example, which is a synthetic remote sensing data. So this is kind of like our radio cubes. You have a position, and then along the other axis, you have a set of frequency channels, right? So if you were remote sensing on the planet, right, these would be different materials, you know, and you can see this, we have different shapes and sizes and relative materials here. And then you have some crossing in the velocity space, which can generate confusion. So this is our synthetic data set where we know exactly what the true classification is. We can test our approach. All right, so this is what happens when you apply a self-organizing map. Self-organizing maps are iterative. So in each iteration, it reduces the neighborhood of things that are considered in the optimization function of building that graph. So for each iteration, you have this fixed input lattice. In each iteration, these points are moved around based upon their neighbors. And over here is showing the neighborhood influence. And as the graph forms and grows, you see it becomes more and more stationary. And the influence that's setting those small changes in the points shrinks to become very small. And at some point, they stop changing completely. Okay. So here's what happens. We take our clustering approach. Here's a self-organizing map. And what you can see from the other example is that now in that lattice, those groups became well separated. Once something is well separated, then we can cluster it using our favorite clustering approach. So in this case, it uses walk trap. Walk trap is this basically what it sounds like. You have random walkers that walk across the graph looking for sub-communities. And when you have communities, they get trapped in those communities. So that is how you identify the clusters, this walk trap. Okay. So up here is a metric, the adjusted rand index, which indicates how well our clustering did. 0 is totally random assignment between clusters. 1 is perfect, correct answer. And we're at 0.66 here, right? So that's not bad. You can see visually that it's messing up a bit on the real data. But there's also another problem, which is that the lattice of self-organizing maps is rigid and still requires some parameter settings. Are you guys still following me? This is a really long rabbit hole of eventually getting to clustering. All right, so then we had this idea. What if we take the self-organizing map where we have a good statistical framework for the lattice and the evolution, and we combine it with a much more flexible dimensionality approach. This case is UMAP. Have you guys heard of UMAP? Some of you. What about TS&E? Okay, good, more of you. Yeah, so these are very common dimensionality reduction approaches. UMAP is on the left, TS&E is on the right. These, in my view, are relatively harmless and very useful approaches. If you have some new data, it's high dimensional, run one of these things on your data, and it will allow you to map your high dimensional information to a two-dimensional space. Where you can get into trouble was the clustering component of it, but as an exploration thing, I highly recommend this. It's really easy to apply to data. It can be very informative for looking to see what things are similar, what things are not. This is MNIST. These are a set of handwritten digits. So these are literally, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It separates them really nicely, okay? Okay, and my postdoc, Josh, has been working on this for a while, and he had developed a way to parameterize the clustering on this particular graph really efficiently, okay? Okay, so now we combine the best parts of UMAP and the self-organizing map, basically substituting one graph for the other, and we get this result. So SOM on the left, you saw before, this new approach on the right, you can see why it's so much more flexible. All right, so now the graph can actually move around your projected space, right? You don't have these fixed distances. And you can see, even though this is pretty obvious to cluster, you can see these clear boundaries where you have no connection, right? That's a good place to cluster, to group things. Here, things are really well separated, okay? So it's much more easy to cluster our new flexible graph. All right, when we do that, now we get an adjusted rand index of 0.9. So this is a significant improvement Still messing up a little bit, but actually much, much better. All right. So where are we here? Okay, here's a summary of what we've done. We learned the prototypes of our spectral cube. We construct a high dimensional and low dimensional graphs where the vertices correspond to prototypes. The high dimensional graph represents density, low dimensional graph encodes distance. We cluster these two graphs. There are pluses and minuses of both of those spaces, which is why we're using both of them. We back propagate the cluster labels by inverting the data back from the prototypes to the raw data. And then we inspect our clusters using noise statistics to determine, are these clusters meaningful or are they just noise? Okay, so finally, back to the real data. So here is L1688 again. This particular data cube has 40,000 pixels where each channel, each set of point here has a spectrum of 749 wavelengths or frequencies. When we apply the prototype learning, we get 341 prototypes. So 40,000 to 341 is a much, much better situation, okay? Okay, so here is the embedded two-dimensional representation, again, using this UMAP SOM framework. What we've done here is we've projected the spectral properties that characterize these prototypes on it. So this is moment 0, or the intensity, moment 1, bulk velocity of those spectra, moment 2, velocity dispersion. So what you can see is that it is very well ordered across these properties. We haven't told it about these properties. These are just inherent properties of the spectra of the data that we're working with. But the fact that there's order is very good. When there's not order, when you look at these things and there's not order, that means there's some kind of twisting, something has gone wrong in the projection to the 2D space. Here, things are looking good. Okay, so now we cluster our graph. And here are the projected clusters on this graph. This is the projected clusters on the region. All right, so first check, clusters are spatially coherent. Now I love this because we have not given the algorithm any spatial information. We just gave it the spectra and we said group them for us. So that means that it's finding the similarities authentically. So you can see you have these peaks, like the pink ones right there, and you have some ranged behavior where the spectra are evolving as they should, right? You have maybe a denser collapsing region embedded in a more turbulent or diffuse region. The interesting thing about not giving it spatial information is that we can identify similarities across discrete regions. So we have parts like in the upper left where we have 2 peaks, but we can see that the similarities, the physics of those peaks should be the same because they're in the same cluster, even though they're well separated. At the same time, those peaks are different than the 2 similar peaks down here, as it should be, right? So this method is picking up some underlying information we haven't given it and showing us something new. So just for reference, this is what that graph looks like in the 2D space, right? So you can kind of see how things are connected. All right, so let's look into a couple of these clusters. All right, so in these pink clusters, we got this pink one here, this blue one a little bit further out. What we're seeing is that this clustering is cleanly capturing the evolving nature of the spectra. You see there's a factor of 2 in intensity, and you can see there's some different significance in those relative ratios there. So in fact, those are multiple components along line of sight. So if you have, well, if you have 2 things along line of sight, and then you sharpen them, you will determine, right, if you can apply your method, you actually see there's 2 things and not 1 thing. If you're paying attention here, this is the raw signal in the blue, and this is the average signal in black, all right? So we've taken something that is much noisier, and now we've sharpened it with a very high signal to noise. So let me show you a more extreme example of that. This sort of olive material, this encapsulating this denser, brighter stuff. Here's the raw signal, right? you can see that this data cube has a signal to noise about 0.1 Kelvin. So if you're a radio astronomer, you would say 3 sigma is my cutoff, remove all this junk, only focus on the bright things. But what we've been able to do is basically intelligently stack the data. So now we can get signal at a rate of 20 signal to noise for our new signal, rather than just 2, right? So now we can actually extract information about the dispersion, the velocity components, and actually determine what is happening in this region that we otherwise would have just left alone, right? Just thrown out. Okay. So this is where we are. We can now apply this to different regions. This is B18. You can see what the embedding looks like. And there are some interesting ways in which the data sort of mirror parts of how the embedding is very elongated. You can see that there is, without seeing, there's a flow here that is clusters up here in the top right. There's more similarities, there's pink-red, then clusters down here and there's blue-green. So if you actually look at the spectra, there is a velocity gradient across that, and this is being picked up. And then you can see that in the organization. This is NGC 1333. This is a very messy region. There's a lot of outflows here. So you get these kind of V-shaped areas. You can see that some of the outflow regions, again, you have similar material that's physically disconnected, this disjoint, but is still very similar. And that a lot of this is being picked out from the noise, this very intense noise background, right? Anything that's not gray is signal. And so that means we can analyze it, right? It actually has inherent line that we can fit and extract properties. This is Orion. Again, Orion also has a velocity gradient, and you can see that there's a difference between the north and the south component of the cloud, right? You have these blue and orange prevailing structure at the top, and you have red and yellow and green at the bottom. Okay, so now we can go back to the data and we can extract more information about what is actually happening within these regions and throw out less information. Okay, so unsupervised takeaway. All right, we developed this new approach, MPEC, which is robust and expressive. That's the key point of having this flexible lattice. It allows us to approach spectral data clustering with the strengths of both self-organizing maps and UMAPs, so the best of both. The number of clusters is set statistically by the data properties. You can look at our method paper if you care about that. It's a bit technical, but we're not putting that in. This is dangerous right here, or I should stop walking around. Okay. The other thing is that we've used this prototype approach to enhance signal to noise, and this allows us to apply this very efficiently, very fast, right? This is very computationally efficient. And the bonus is that with these prototypes, we get a very clean identification of clusters, which allow us to cleanly fit multiple line components to look at flows and other features in very low signal to noise regions. So I want to say that we apply this to radio cubes, but whatever your favorite spectral data is, for example, Gaia data, it works on that. It doesn't care about spatial correlation. It doesn't need that information. It's just looking at the similarities between vectors, right? There's just nothing special about radio data here. So this is an embedding of white dwarfs in Gaia. This is a project that Keith Hawkins and a student are working on. They're looking at polluted white dwarfs, right, to try and understand if these white dwarfs may have engulfed planets. And you need to classify these white dwarfs in some way. And so this is potentially allowing us to identify these things and cluster them. All right. So I still have some time. So I want to say a few words about the rest of the machine learning work that I'm doing, which is my administrative work. So as mentioned, I'm the director of the NSF Simons AI Institute for Cosmic Origins. We are 6 months old, and there's a collaboration of UT, UVA, NRAO, SLAC, and WarLab, and UCLA, right? Okay, so what is our mission? We aim to develop transformative AI methods to meet pressing astronomical challenges. And in this mission, we've identified 4 astronomical challenges and 4 fundamental AI themes that we're trying to push on: trustworthiness, efficiency, interpretability, and robustness. These are just classic machine learning things that are important for a wide variety of problems. And our goal is to serve as a nexus of collaboration to increase the accessibility of astronomy and AI data through open source AI-powered tools, data sharing, and AI educational initiatives. So I know this is a very core theme of the Flatiron, right? Open data, collaboration, community resources. And so there's clearly a lot of synergy between what we're trying to do and things that are happening here. And I know there's a huge amount of AI happening here. So hopefully you can tap more into that. But in terms of the vision, what we're trying to do is enhance the astronomy research cycle, right? You have a person writing a proposal to take observations, the data is collected, calibrated, reduced images, then delivered to the user, and then stored, and then eventually goes back into the process, get more data, or analyze the data. Or you might be writing a computing proposal to run simulations, which again gets stored and goes back to the data, the user. Okay. So in our 4 themes, we have AI trustworthiness, right? The goal is focused on the trustworthiness of generative AI models, including multimodal language models, a very popular topic right now. And we want to answer the question, how can we use these models to do scientific research? So this is something that industry maybe thinks a bit less about. They care about profit. We care about information. And so just because industry is working in this space doesn't mean they're doing something that's useful or effective for us. So we're aiming to look at the areas where astronomy workflows can be improved with these models and see what we can do. But this is fast, very fast evolving. So, what we said in the proposal will probably not be what comes out at the end in 5 years, but it'll be fun either way. The next one is AI efficiency. This is really being led out of NRAO. They're preparing for next generation facilities, next generation VLA, extended ALMA. We're talking about trillion voxel data cubes. So these are not things you can download onto your laptop, right? So they're concerned with how do we process this and how do we deliver products for the user, right? So given that you can't maybe download the whole thing, you want to know where is the interesting things in the data. And so this is where things like MPEC might come in. We identify interesting features in the structure, and then that's delivered to the user as part of the products to say, here are some interesting things you can look at. All right. The next one is AI interpretability. This is working in the space of simulation-based inference, and there's collaboration with the DREAMS collaboration, which is also here. So I think this is building out our partnership along those lines. But we're particularly focused on how we can use AI to infer underlying cosmological parameters, such as the nature of dark matter. And the last one is robustness. We call it the accelerated universe. And so this is how do we train surrogates, so neural network models, to model physics. So this is, in some sense, a holy grail, because directly solving equations is very expensive, as we know. But there are a variety of different methods that allow us to take shortcuts, maybe through a lower dimensional latent space, to get to a solution much more quickly. And it runs on GPUs. So this particular approach is focused on how do we build robust surrogates for physics problems with a particular focus on astrochemistry. Okay. So last is just to say, we've been doing a huge amount of things. We have our first annual conference next week. We'll have a conference every year. Hopefully you will go to our website, sign up for the mailing list, participate in other conferences that we have. We have a huge amount of training and community interactions that are going on. At the same time as there's the conference, we have an AI Astro Intensive Bootcamp. So this is mainly intended for students, but could be postdocs and people looking to apply machine learning methods to their data, basically using astronomy data sets. We're partnering with TAC. So it's an intensive, hands-on, interactive training on AI methods. We also have a seminar series. I know we have so many seminars to go to. We've made it every other week, but you can also be up to date on what's going on there. We have this AI certificate program, which is going to be launched in a couple of weeks. So it's very important for us to upskill the community. And that means doing so rigorously at the graduate level. And boot camps are great, but they're not hardcore if you're trying to really dig into the details. Moreover, boot camps and summer schools are nice because you learn from them, but they're not accredited, right? You don't have transcripted credit. They may not be recognized by industry. The certificate program is built on a Masters of AI. And so this is actually an online program that people can register for and take these courses, get actual accredited graduate classes, which could be transferred to their institution if they're a graduate student, or otherwise it can be part of their training that's actually a recognizable credential with industry. We just finished our annual call for seed proposals, so we're hoping to put in funding for new exciting things that align with the Institute initiatives. And starting this winter and next summer, we're gonna have the first undergraduate focused Astro AI schools. Okay, so this brings me to my summary. Robust clustering is critical to fundamental star formation problems with all of the acronyms: star formation rate, star formation efficiency, core mass function, IMF, right? We need clustering to actually get a handle on the blob. Supervised methods are great. They can perform fast, complex pattern matching, assuming you have a well labeled and large training set. If you don't, unsupervised methods, particularly these graph-based methods, are really powerful. And if you really harness the statistics underlying these frameworks, you can move towards a parameter-free, data-driven approach to clustering, right? And last but not least, we have MPEC. This is this new prototype learning approach that provides this cleaner, high signal to noise view of data that uncovers hidden trends. We're working on the method paper for this, and we hope to release the code base hopefully within the next 6 months. So at this point, thanks for your attention, and I'm happy to take questions. Yes, go ahead.
Well, lovely talk. I'm a lot of details that I didn't know. I was wondering, so you showed in the end that this was also applicable, or the unsupervised method is also applicable to Gaia data and to other data. I kind of wondered, where does it stop? When do you think it's no longer applicable, or where would you say, okay, maybe hold off to kind of using this kind of approach, or do you say no, actually just go and apply it to whatever that's you need?
Yeah, well, I tend to think that dimensionality reduction is of any type, whether it's UMAP, TSNE, self-organizing map, it can be very useful because it gives you a new view of the data. It doesn't add anything to the data. You're not putting in physics or biases. So I always recommend the new data set, just play around with some of these things. Clustering is where you get into trouble, which is why we have this very intensive push to do this really rigorously, which is maybe not so exciting for this sort of talk. But clustering is where you say, okay, do I want to group? Do I need to divide things into categories? Do I have a semi-supervised problem where I know some of the things and I want to attach labels to other things? Then this kind of clustering approach can be very helpful. And so I would recommend it for that. You want to make sure, though, that in the end, you have this human looking at the clusters and going back to the physics and saying, what am I really learning from the spectra in this cluster? Because again, we haven't added anything to the spectra. We're not putting in information. And so it comes down to you and just saying, how can I make use of this new view? I don't know if that answers your question, but yeah. Mm-hmm. Yeah.
Thanks, Bob. I had a question about MPEC, I guess, or prototype learning in general, maybe, which was, I missed why that was a step. Like, why is it not sufficient to like randomly downsample your data if you think it's not, if you think it's representative of the types of data that you want to apply to?
Yeah, if you just randomly downsample it, then you still have your noise issue. And so you still have noise, right? And so if you're, The prototype is giving you an intelligent way to average the information.
I see.
And so you're, instead of just subsampling it, you're actually averaging. And so that, again, gives you a cleaner view of the data, and the prototypes in particular give you this graph. So there's a whole area of statistics of vector quantization. So one of the things that comes out of this is a graph. And as we saw, using these graphs can be very powerful for doing other things like clustering. Yeah, so those are the main reasons. Yeah. Nobody's asking the important question, which is why are your cats so cute?
Why are there not more cats?
I know why they're not more cats. Sometimes I can't tell if there's two or one cat. They're always together. Yes.
Just a question about your slide showing your picture for the AI center you're running. For interpretability, you mentioned cosmological parameter inference, and for robustness, you mentioned astrochemistry. Do you think these are the two fields which are most relevant in these two areas?
No, not necessarily. There's only so much you can do with a limited amount of money. And both of these areas seem to be important, either important bottlenecks in the case of astrochemistry, or really, really important application cases, as in the inference case. And so both of these, if you can solve these problems, you can make really important strides within astronomy, which is why we picked them. I think the other ones, the large language model and the observable group, which is doing data optimization, essentially, those are applicable to a broad range of fields. And so the idea is we're not just limited to those two science areas. Those are kind of some interesting grand challenges, but the other fields will also touch on anyone who's working with radio data, NRAO. We have people working in LoRa Lab, the multimodals, and we tapped into DESI collaboration and so forth. So, yeah. Yes, Rolf?
Should I use this?
Yeah, presume.
Okay, Stella, thanks. This is so cool. I was wondering whether your approach can be used to engage in the feature important stuff. Because, let's say when we use James Webb to either identify individual stars or star clusters, there's always the question which filter should we use if we have a photometric approach to be most telling. And so we have been using normalizing flows to address this question. And it seems to me that your clustering approach can also make important contributions to, to this field. And for Gaia, which Gaia Spectra should use, which lines should you use to, disentangle white dwarfs, polluted white dwarfs, and other features. And so, have you thought about these things?
I haven't. In addition to the clustering, we're doing this post-processing phase where we're using actually time series analysis to look at the signal more carefully. So basically trying to decompose it into signal and noise or structured noise. And so that is another step that allows us to fit and clean up the signal and sort of maybe focus on some more interesting things. But we haven't looked at significance in the way you mean. I mean, the easiest way to do it is just, maybe give it like half the data cube and then see, or one spectral line and then see if you're recovering the clusters. But I haven't thought about it in that way. No.
Exactly. I think that is the easiest approach, but you can also use, let's say, feedback library divergence to assess an importance to a specific feature. And
yeah,
it is very promising, in particular when you link that then back to future observations and you want to optimize your approach.
Yeah, that's a good point.